So the first topic is design flow in application specific integrated circuit. Okay. So the diagram which is shown here is the design flow. In design flow, you have this much of steps. The first step is system specification, architectural design, functional design and logical design, circuit design. So combined together, all these four steps are classified as front-end design. Next is physical design, or you can call it as a layout design or backend design. Okay, so physical design can be further has lost. It has four steps. One is physical verification and sign off, and then fabrication, packing and testing, and then chip. The last one is a chip, which is nothing but an IC, which is shown here in the diagram. Okay, so uh, this is how an IC is fabricated. So by following all these steps, an IC is getting fabricated. You can see here from system specification. So this is the first part of design flow, and then it goes to the software, and it's converted into a circuit, and that circuit has to be reconfigured for the layout, and from that it has to go to fabrication unit, and in fabrication unit the physical form of an IC gets shapes, and then it comes out as an IC. So in between this you have a lot of steps. Okay, this is just an idea of an ASIC design flow. It's an abstract of an design flow. Okay, we are going to understand what are the steps involved in it, but if we get deep into it, each and everything is a big area. System specification is a big area, designing is a big area, architectural design is a big area. You have a lot of tools for it, and you have a lot of methods to it, and you have a lot of simulation tools available. Each and every industry just one particular application also. If you want to design IC, it does not mean that everything is done only by a single company. They give it to another company. They may be doing only one part, and they may be that may be given to another uh, subsidiary, or it may be given to another project within the company itself. They may be concentrating only in testing. They may be concentrating only in analog design. They may be concentrating only in digital design. It's like that you have a lot of sub classifications, and it's very wide. Okay, so in this particular class we are trying to just understand, we are just trying to going to explain what is really uh, the abstract of a design flow. Okay, the first one is system specification, which I mentioned you. We'll now move on one by one. Okay, the next one is the first one is system specification. So in system specification, what they do is that I told you that this is nothing but an IC fabrication, that's all. So in IC fabrication, what they do is that they first specify the IC, which means that what is the total area of an IC, what is the total power of the IC. I'm speaking only about the term that is total. Okay, it's about the whole. It is not about only one particular block in IC. It's about the whole area of an IC, which is mean that this system specification clearly defines the boundary beyond which it cannot be done. Okay, so they clearly define my size of an IC should be 1 into 1 centimeter, or it can be 1 into 2 centimeters, and then they will be defining by the IC which I going to market will be having the power consumption in terms of uh, microwatts or nanowatts. Most probably it will be in milliwatts. Okay, if you take one microcontrollers, it will be in milliwatts. Microprocessor will also be having the power consumptions in milliwatts, and then that is an idea. That is what they will define it. Okay, so that they will define it. So that comes under the classification of that is what is given in system specification. Okay, to start an IC, you require the system specification. So in system specification, generally what who will define it? The company will define it. The company which is going to market the IC. Here, we have a lot of companies. You have Intel, you have AMD, you have Philips, you have Motorola, you have Texas, you have ST, and then you have Arduino, you have Atmel, you have a lot of PIC, you have a lot of microcontrollers. Um, yeah, a lot of microcontrollers are available, a lot of processors are also available. Okay, so In that the company will specify what is the in which application they are going to launch it, which means that they can use that application, that IC, to an DSP based application, or they can use it for cloud computing based application, or they can use it for IoT based application, or they can use it for um, mm, controller or any specific applications. Okay, so they can use in that way, so that the specification will be defined by the company. So they will define this much of power and this much of area, which is the overall, which cannot be expanded. Okay, the company has to, whatever, that will be the limit which cannot be compromised, or which cannot be, it can be less than what they define, but it cannot go beyond what they define. Okay, so that is what they will define, and that is nothing but system specification. And as I told you, that they will just give the outline and boundaries of what they want as a product at the end. So that is what is given in the system specification. Okay. Next one is architectural design. So if you take the architecture, so in architecture you have a lot of architectures. It may be analog design, or it may be a digital design. So basically you have only two architectures. So if it is going to be a digital design, then you have to use RISC or CISC. If it is going to be analog, you have to use floating point units, and then you have to define your ALUs and others. Okay. So if it is going to be a digital, then it is going to be having RISC based ISA, which is nothing but industrial what is instruction set architecture. RISC means that it has less number of instructions. CISC means that it has more instruction, which we generally say it as complex instruction set computers. Okay, so this is the trend as of now. We have only RISC, and the CISC are getting less in the market. So they're getting slowly degrading, or we can say that slowly they are moving away from the market. The best example for RISC will be ARM. So in ARM, you can see a mobile processor, you have desktop processors. Every processor that are getting developed now are based on RISC architecture. The CISC architecture is the old one, which is nothing but it is done by AMD, by Intel. Still they use the CISC architecture. Okay, so generally this is classified as x86 series. Okay, x86 is nothing but CISC based architecture. So RISC is a reduced number of instruction. You have the complication in designing will be less. That is a main idea behind architectural design. It will be very less complications. They have less complication. If you take complex instruction set, it will be more complicated. If you take RISC, it will be we cannot say that it is not complicated. It is also complicated, but when compared with the instruction set of a CISC, the RISC instruction set has less complexities. In that way, RISC is more better. It is power efficient. It is very wise. It can be scalable. It is reliable, and you have a lot of advantages of RISC based architectures. So that is about the architectural design. Okay, so in general, the first one, the company defines what is the outline of IC that they expect, and in that they will give you the inputs, whether it's going to be a, analog applications or digital applications, and defining that, by defining that, they will go with the RISC or CISC or anything that is done. If you take for example, for analog, you can take ADC. ADC is an analog type of an IC, which you have only the successive approximation techniques. It will involve some digital concepts, but apart from that, analog is very important in that, because it is used to convert the analog value into a digital value. So you need that, and analog devices, analog equipment, analog circuits to be done there, to be fabricated there. So that is architectural design. Next is behavioral or functional design. Behavioral or functional design. So what is mean by behavioral or functional design? In the first part, you have defined what is the overall requirement. In the second one, you are coming for architecture, and then the third one is functional design. So this is nothing but writing a program. In a simple way to understand, in a simple sentence, if I have to make you to understand, this is called the writing of a coding. Functional design. Okay, they will define from here. They will define for each and every sub element or sub part in a circuit. They will define what is the area and what is the power. For example, let us take microcontroller. In the microcontroller, you have clock circuits, you have ADC, you have timer, you have counters, you have cache memory, you have RAM, and then you have registers, and then you have ALUs, and then you have floating point units. Like this, you have more number of sub blocks within a main block. Okay, so for each and every sub block, what is the overall power? What is the overall circuit delay? What will be the overall time, what will be the power, area, and everything will be defined. If you take the first one, this first one, if you take the first one, here you will be defining overall, it can be 10 milliwatts or 10 nanowatts. In the 10 nanowatts, we have to define how much nanowatts is used for one particular block, how much area is used for one particular block of sub block which is there in the circuit. Okay, so that is this one, and that is behavioral or functional design. So that is about this functional and behavioral design. So I'm not reading it in general, I'm just explaining you, and you can just have a read over it, you can understand it much clearer. And then next is a logical design. So in logical design, what you do here is that you will write the program. As I told you, you will be writing the program. So the program will be you can write the program in two different ways. That is, either you can use Verilog or VHDL. Okay, but in general, you will be writing a program. So that program will be based on hardware description language, and in that hardware description language, it may be a VHDL or Verilog, and then generally we declare it as a RTL, register transfer level. Okay, which means that in high level you are writing a program, you are writing a code, it may be a C based. Generally this Verilog and VHDL comes or falls under the category of object oriented coding, which means that C based codings. So VHDL and Verilog are object oriented codings, but this is specially used to write the coding only for electronic circuits. You cannot write a general program as you write it for any other applications for like web design or any other thing. So you cannot write in that way. This is specially used only for doing an IC. So this program, this software or this tool or language, this programming language helps to do the process of only how to code a application that is relevant to a hardware. Okay, so in hardware you can see it physically, but if you want to make it to a hardware, you have to write the code, which means that you have to write it in terms of program, and that program has to be converted into circuit, which is nothing but the next one of this one, which we will take it in the next class. Okay, so now as of now we'll just try to understand what is this logical design means. So this logical design means that writing a program, that is logical design. So at the time of writing a program, you will be writing the program for functional verification, you will be writing the program and you will be simulating it. You can use expressions, you can use the k maps and other things can be written, and it can be verified, it can be synthesized, and it can be simulated. So in general, the logical design is nothing but writing a program for whatever application that you have taken. So if you take a simple application, so I told you that the microcontroller, in that you have lot of sub areas. In that, each and every sub area has to be written in the form of a program, and that program is written either in the form of Verilog or VHDL. Okay, so that is the idea of this logical design. Okay, with this I think we'll be trying to complete this one. The next class we'll follow this the remaining part of the specifications. Okay.